Yes, children. So, assuming the fact that you people have studied about Dalton's atomic theory, properties of cathode rays, properties of anode rays, and then Thomson's atomic model and Rutherford model, all these things you have already studied in 9th class. So, assuming this, I am proceeding further with the structure of atom. That is developments that have taken place leading to the Bohr's model of atom. So this is what we are going to start with. So I have just given a brief introduction about how Bohr's model of an atom came into existence. You know very well that the limitations of Rutherford model led to Bohr's model. Now here, interaction of radiations with matter, any radiation when it is hitting the matter, this provided immense information regarding the structure of atoms and molecules, and it was Bohr who utilized these results to improve Rutherford's model. And the major developments which helped Bohr to formulate his model of atom was that the electromagnetic radiations, they show dual character and atomic spectra. So these two things you will try to understand now further when we go ahead. We will see about what is electromagnetic radiation and all that. Atomic spectra, everything we will go into detail. Now, James Maxwell was the first to give a comprehensive explanation about the interaction between charged bodies and the behavior of electrical and magnetic fields on a macroscopic level. What is the interaction between charged bodies and its behavior in electrical and magnetic fields? Now, he suggested that when an electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted in the form of waves. And these waves are called electromagnetic waves or electromagnetic radiation. And sunlight is an example for electromagnetic radiation. According to Newton, light was made up of particles. Only in the 19th century, wave nature of light was established. Till the time, it was not understood. Only in 19th century, wave nature of light was established. Newton was considering that light was made up of particles only. Till that time, everybody was thinking that light was made up of particles. But in 19th century, they came to understand that light behaved as a wave also. Now, what are the properties of electromagnetic waves? Now, let me show you just a simple example which is given in your NCERT text. Now say this is the direction of propagation of light, and I told you it is associated with electric and magnetic field. It's having both magnetic field component and electric field component. So the direction of propagation of light and the magnetic field component and the electric field component, they all lie perpendicular to each other. So this is the main thing that you have to understand. The oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of the wave. So all three of them, they are perpendicular to each other. So this you have to understand. Right? Okay. Now let us see what are the properties of electromagnetic waves. The electric and magnetic fields produced by oscillating charged particles are perpendicular to each other and to the direction of propagation of the wave. This is the picture that I showed you just now. These EM waves, that is electromagnetic waves, they do not require a medium to propagate and can move in vacuum. They do not require a medium to propagate. This is a very important characteristic feature of electromagnetic waves. Electromagnetic waves are of many types which differ in wavelength or frequency. Any one parameter, if you consider, they differ in wavelength or frequency. And the arrangement of these electromagnetic waves in the decreasing order of frequency or increasing order of wavelength is called an electromagnetic spectrum. How these electromagnetic waves are arranged in the decreasing order of frequency or increasing order of wavelength, that is what is called as electromagnetic spectrum. Now this is the electromagnetic spectrum. This is given in your textbook. Now you see here, this is nu, that is measured in hertz, and this is lambda, which is measured in meter. Lambda is the term used to represent wavelength, and nu, it is nu, is used to measure, is used to represent frequency. Frequency is measured in hertz, and lambda, that is wavelength, is measured in meters. Now you see here 10 power 9 to 10 power 24, that means decreasing order of frequency, and here you will find 10 power minus 16 to 10 power 8, that means here it is increasing order of wavelength. So all the electromagnetic waves, all these are electromagnetic waves. You see here gamma rays, X-rays, UV rays, then this colored lines, it represents visible region, then infrared rays, microwave, then FM, AM, long radio waves. FM, AM, you must have heard, they are radio waves. All these things are electromagnetic waves. How they are arranged? They are arranged in the decreasing order of frequency or increasing order of wavelength. So the set of electromagnetic waves which are arranged in this fashion, in this order, is called an electromagnetic spectrum. Now here we are considering only the region between UV rays and infrared rays, which is called as visible region. Why visible region? Because the wavelength corresponding to this visible region is visible to naked eye. That is why it is called as visible region, and the corresponding spectrum is called as visible spectrum. So here the visible spectrum, it ranges between 400 nanometer to 750 nanometer, and remember 10 power 9 nanometer is 1 meter. So this is what you have to remember. Now see, this is 750 nanometer, wavelength is high, and here it is 400 nanometer, that is lower wavelength. That is why I told you increasing order of wavelength. So from 400 to 750 nanometer, the wavelength ranges in the case of visible region. So this is your visible spectrum. Now what are the different what other characteristic feature you can say? Unlike sound waves or water waves, electromagnetic waves do not require medium and can move in vacuum. This I already told you. So these are the characteristics of electromagnetic waves. Okay. Right. Now what are the different, how are they characterized? What are the properties which characterize an electromagnetic wave? So let us see that. Right. Now what are they? They are wavelength. Wavelength is given by the symbol lambda. This is wavelength. Now what is wavelength? It is defined as the distance between any two consecutive crests or troughs. Like say this is the axis, you are showing a wave like this. The region above the axis, they are called as crest, and the region below, they are called as troughs. Now this is a trough, this is a trough, this is crest, this is crest. So the distance between any two consecutive crests, that is between this and this region is called wavelength. Same way between two troughs, this is also called as wavelength. And how do you express? It is expressed in angstrom units. You write it as like this, or you may represent it in meters, or you may represent it in centimeter, or even nanometer, or even picometer. PM means picometer. Now what is the relation connecting all these things? 1 angstrom unit is equal to 10 power minus 8 centimeter. That is equal to 10 power minus 10 meter. Then 1 meter, 1 nanometer is equal to 10 power minus 9 meter. Same way, 1 picometer is equal to 10 power minus 12 meter, or 10 power minus 10 centimeter. So these relations you are supposed to know. So this is one characteristic property. Then the second one is frequency. Frequency is denoted by the symbol nu. What is frequency? Frequency of a wave is defined as the number of waves passing through a point in 1 second. Number of waves passing through a point in 1 second. This is called frequency. And this is represented in hertz. 1 hertz is equal to 1 cycle per second. This is called as frequency. Then the next one is amplitude. Now what is amplitude of a wave? This height between the axis and the crest or the trough is called as amplitude. So you can say amplitude of a wave is the height of the wave. height of the crest or depth of trough. This is called as amplitude, and this is also represented in the units of length, that is meter, nanometer, like that, and it is represented by the letter A. This is amplitude. Then the next one is wave number. Now what is wave number? It is defined as the number of waves present in 1 centimeter length. The number of waves present in 1 centimeter length. So evidently what you understand, this wave number, which is given by the symbol nu bar. Nu bar. This is how we represent wavelength. So nu bar is equal to 1 upon lambda. So whenever you consider a wave, it is made up of one crest and one trough is a wave. One crest and one trough, this is a wave. So the number of waves present in 1 centimeter length is called as wavelength. That is why nu bar is nothing but 1 upon lambda. Okay. Now, based on these characteristics of waves, you can understand what is the relationship between wavelength, frequency, velocity, and all that. Okay, there is one more, that is period, which is represented by the letter T. This is the time taken for one wave to pass through a point. This is called as T, and it is the reciprocal of frequency. So you can guess now what will be the relation between T and frequency. So T is equal to 1 upon frequency. And when you want to say what is velocity of a wave, what is velocity? Velocity of a wave is defined as the linear distance travelled by the wave in 1 second. So velocity is nothing but distance upon time taken as in speed. So distance travelled by the wave in 1 second. This is called velocity, and this is expressed as c. And what is the unit? Unit of velocity is centimeter per second or meter per second. This is the unit of velocity. Now, what is the relationship connecting velocity, wavelength, and frequency of a wave? Frequency is nothing but the number of waves passing through a point per second. And what is wavelength? Wavelength is the length of each wave. So the product of frequency and wavelength should be equal to velocity. So velocity, that is c, is the product of nu and wavelength. So this is the relationship connecting these three. Then time period is inverse of frequency, that is reciprocal of frequency, and velocity is equal to frequency into lambda. Then what is nu bar? Nu bar is nothing but 1 upon lambda. So these relations you have to be very clear. Now once you understand all these things, now let us consider what are the limitations of this electromagnetic theory. What are the limitations of electromagnetic theory? Now when this electromagnetic theory was established, that time these electromagnetic waves, they were established to show dual character. Now what is this dual character? Particle character, which was established by Newton, and wave character, which was given by Bohr. Now particle nature is proved by black body radiation, this proves particle nature. And also photoelectric effect. So these two properties or characteristics, they exhibit particle nature of the electromagnetic wave. And to describe wave nature of electromagnetic waves, the characteristics are interference and diffraction. So this we will see later, or probably you will see in your physics. So let us just give a brief note on black body radiation and photoelectric effect. Now what is this black body radiation? Black body radiation is nothing but if any substance with a high melting point is heated, say an iron rod is heated, first it will turn red, then it will turn yellow, then it will turn white, and then it will burn with a blue light. You must have seen in your gas, the gas top is made up of iron, so the flame that is coming out is blue flame, is it not? If the substance being heated is a black body, what do you know about black? It's a perfect absorber and also a perfect radiator of energy. So this black body can emit and absorb all frequencies. Okay, so this is what is called as black body radiation. The radiation emitted is called black body radiation. But black substance means it can absorb as well as emit. And the emitted radiation is called as black body radiation. That is, the energy emitted by a black body is called as black body radiation. So this much if you understand, that is good. So the nature of emission of radiation from hot bodies. So this is what is called as black body radiation. Now if you consider it in terms of frequency, what we saw in the electromagnetic spectrum, it is electromagnetic spectrum, it shows decreasing order of frequency and increasing order of wavelength. Okay, and where do you see the blue color in the electromagnetic spectrum? Electromagnetic spectrum, the blue color is having lower wavelength and red is having higher wavelength. If the wavelength is higher, then the frequency is lower, and if the wavelength is lower, then the frequency is higher. So wavelength higher means frequency is lower. So this relation you are supposed to remember always. So what they say here is red color lies in the lower frequency region, while blue color belongs to higher frequency region. Okay, blue color is here lower wavelength, so higher frequency region. This is higher wavelength, and so this is lower frequency region. Okay. So this is what you should know about black body. Now let us come to the next one, that is photoelectric effect. Photoelectric effect. Okay. Now what do you need to know about photoelectric effect? It was in the year 1887 that Hertz performed an experiment. What was the experiment that he conducted? He made, look at the figure that is given in your textbook. This is a metal surface, and light was made to fall on the metal surface. And what happens when the light is falling on the metal surface? The metal surface, the atoms which are there on the surface, they will eject electrons, and the electrons will move here, trigger the battery and the ammeter. It shows that the flow of electrons, and then it is detected here. So he said that electrons were ejected when certain metals were exposed to a beam of light. So this is called as photoelectric effect. This is what he told that. This phenomenon is called as photoelectric effect. Electrons are ejected when light of a particular frequency is made to fall on a metal surface. Electrons are ejected. So this is what is called as photoelectric effect. Now what are the necessary conditions for photoelectric effect to be observed? The electrons are ejected from the metal surface as soon as the beam of light strikes the surface. There is no time lag between the striking of light beam and the ejection of electrons from the metal surface. Now the question is, any light which is made to fall on the metal surface, will it eject electrons? This is one important question. So there is a minimum frequency of the light radiation. It should exceed the frequency of the electrons. Then only the electron will be ejected. Otherwise, electron ejection will not take place. So that is what we are going to see now. First one is electrons are ejected, of course. When it will be ejected? When the frequency of the light radiation, if it is greater than that of the frequency of the metal electron, then only electrons are ejected. See here, for each metal there is a characteristic minimum frequency called nu naught. This is also called as threshold frequency, below which photoelectric effect is not observed. At a frequency nu greater than nu naught, nu is the frequency of the incident radiation, nu naught is the frequency of the electron. So if nu is greater than nu naught, then only ejection will take place. The ejected electrons come out with certain kinetic energy. The kinetic energies of these electrons increase with the increase of frequency of the light used. The speed of the ejected electron will increase with the increase in frequency of the incident radiation. Then the number of electrons ejected is proportional to the intensity or brightness of light. How many electrons are ejected from the metal surface depends on the intensity or brightness of light. Now, intensity of light is based on amplitude of radiation. I told you light radiation is showing both wave character as well as particle nature, is not. So, wave character means, that is, the characteristic property is wavelength. So, these are the three important points, the results observed when photoelectric effect is observed. Now, it was also suggested that the energy of the incident radiation is directly proportional to its frequency. This was given by the scientist Maxwell. He was the one who told that E is proportional to nu. This was given by Max Planck. This is also equal to E is equal to h nu, where h is called as Max Planck's constant. What is the value of this constant? It is 6.626 into 10 raised to the power minus 34 joules second. This is the value of Planck's constant. Now, coming back to this photoelectric effect, I told you that the electrons are ejected only when the frequency of light radiation is greater than the frequency of metal electrons. So, this relation is shown if the energy of the incident radiation is higher, then the ejected electron will come out with a particular kinetic energy. So, it is shown by the relation h nu. This is nothing but energy of incident light radiation. This is equal to h nu naught. What is this h nu naught? It is nothing but threshold energy. That is energy of the ejected electron. the minimum energy of the ejected electron, that is called as threshold energy. And when this is in excess, what will happen? The excess energy of the incident radiation will come out in the form of kinetic energy. So it is equal to half mv square, mass of electron. This is nothing but kinetic energy, so you can say h nu is equal to h nu naught plus ke. You know very well that kinetic energy is equal to half mv square. This relation, you know it already. So if the energy of the incident radiation is more, then more and more energy will be transferred to the electron, so which will give rise to kinetic energy of that ejected electron. And energy is proportional to frequency. So if frequency of the incident radiation is more, energy of the incident radiation will be more, so kinetic energy of the ejected electron will also be more. So this is what you have to understand by photoelectric effect. So when you have to study photoelectric effect, you can take the observations of the experiment from your textbook, 3 points that is given, that you have to very clearly note. And what is the mathematical relation of this photoelectric effect is this. This is the mathematical relation. Even Einstein was also able to explain the photoelectric effect, because Einstein was one who also understood light in the form of particles. But he also explained Planck's quantum theory also at the later stage. He used that also. So the problem was the particle nature of light. Light is possessing particle nature, and particle nature is only explaining black body radiation and photoelectric effect satisfactorily. But on the other hand, it was not able to explain the property of interference and diffraction. So how to resolve this was to accept the idea that light is possessing both wave character as well as particle character. Only then you can understand that how all these properties are being shown by light. So remember, whenever radiation interacts with matter, any radiation which is interacting with matter, it displays particle-like properties in contrast to the wave-like properties. So when it is interacting with the matter, it will show particle-like properties. Whereas this interference and diffraction, they are shown when it is propagated. So this is how you have to explain the wave nature and particle nature of light. Right?